Thank you. So today I want to talk about counting kind of irreducible polynomials. Okay, we have irreducible polynomials over finite fields, but how many there are? So it is actually a well-known result. So this is from Gauss, maybe. So they count it. Many people count it different way, but there is a nice Möbius thing, etc. But today I want to fix some coefficients. For example, I want x cube, but I don't want a x squared term. So how many degree 3 irreducible polynomial is there kind of? So maybe a higher degree, I want to fix some of them and try to count it. There are some kind of, okay, this is a nice question actually inside, but there is also some application, not much more, but we have also some applications. But this is kind of number theoretical problem over finite fields, but we use algebraic geometry, algebraic curves, singular curves to count them. So it is also related with algebraic geometry. So let me start. So let's take an polynomial. So in finite fields, every function actually a polynomial. So it doesn't matter writing f or p. Okay, so I actually want to talk just two coefficient fix today. And it is the just first two coefficient. And I will just write some terms of the polynomial. And it is going so on. So, and I fix the first one and second one. If you want, you can fix this and fix from here, something doesn't matter. So, but I will just talk about this. Actually, if you want to fix too many, it will get very hard question. So actually, for 3, we can still use algebraic geometry curves, but for if we fix 4 terms, then we can't use same idea. We can't use curves to count these numbers. So okay, so this is inside of a finite field. This is the notation, general notation of finite field with q elements, and this is the means polynomial ring with x. Okay, so it has a root inside over some extension, and if this is irreducible with degree n, we know that we have an alpha inside of degree n extension with there is alpha with f of alpha is equal to 0. And the nice thing, if this is irreducible, this is inside of this, but not inside of any sublink or subfield of this one, or any proper devices. How is my sound is good? Is it come?
Yes, I mean,
okay.
Yeah, I guess we can all hear. Yeah.
Okay, thank you. So we have this one. So in characterization, so finite fields are not hard. So we have FQ here, and the extension is and here. Say we have another D. So here our extension is n, and here just d, and d should divide n. So there are many elements. So here we have q power n elements. Here q power d elements, q elements. Okay, there are some alpha, say beta or gamma, doesn't matter. So some of them is inside of totally here, not any other proper field. And some of them maybe for this one, maybe for other devices, but we have such elements. So we relate this irreducible polynomials with these elements. So if we have such a irreducible polynomial, we can write our polynomial with their conjugation. So we can write this with alpha is the root of this, so x minus alpha, and we just take the q power of alpha, and they are all different, and we have n roots. So if we know one root, and we can actually know the other roots. So this is nice because we express it with elements from fq power n. So I want to just write some terms of this one, especially since I am interested with two terms. I want to expand, so expansion with the polynomial expression. So we have x power n because all of coefficient 1, and we have minus and multiplying with this. So we have basically plus, I will write like this, minus sum of I is starting from 0 to n minus 1 alpha power qi x power n minus 1 plus. And if we want to calculate the second one, we choose two of them, and all of them should be x. So it will be, so if I choose two of them, one of them alpha power qi, the other is alpha power qj. So if we multiply them, it will be like this, and we will multiply different ones, so we can write it like this. And so on. So now the first coefficient is this one, and second coefficient is this one. If we want to make both of them, for example, 0, so this expression should be 0, and this one should be 0. Okay, so in general, actually, we can write all of them. So we denote Tn as alpha. So normally this is trace of alpha, we call this sum. So this is, we call second trace, third trace, kind of. So it is like alpha power qi1, qi n, 0, r1, rn, up to n minus 1. So okay, the coefficient actually change with minus, but doesn't matter. So we can actually understand and check this. So minus doesn't extra big deal. So actually, when we are trying to count this, we just try to understand these elements. But the thing is here, okay, for sum of alpha, this is irreducible. We can do many of this. So this is actually, if this is minimum polynomial of alpha, then it is irreducible. But if this is not the minimum polynomial, still this is the characteristic polynomial. So we will interest characteristic polynomials, all of them, but some of them reducible. So we kind of have like not inductive, but Möbius idea. So I will actually talk about this when I need it. Okay, let's denote. So this is actually maybe in every finite fields book, this proof of this, because it is very nice, and for application as a problem, maybe denote the number of irreducible polynomials. So this is over FQ and DP. Actually, I put this monic. The monic means the coefficient of x power n is 1. The leading coefficient is 1. So we have this one. Okay, let's try to count this. So we have this IQ. Say I just wanna do for all b. For example, let's count this one, for example. We have this one. So if this is a polynomial degree d, and for degree n, we have n roots inside of the field. But if it is irreducible and if it is degree d, it has d distinct root. So if I multiply this with d, I have the elements inside of d, but which has a minimal polynomial of this. And if I add this for all d device n, we will get all the elements here, because all of them has a root of irreducible polynomial, which degree device n. And if one of them is degree d, it has d distinct roots. So if I multiply with d and add all of them, I will get all the elements. So this is nice because this is in number theory basic thing on Möbius using Möbius transform, not transform, I forgot the Möbius thing. So if we use this, so we have this one, this implies by Möbius idea n times, and so generally people call it n, but we call it I, n is equal some d device n, then is d q covers and so on. Yes. And if I take n as a 1 over n here, I count to every number of irreducible polynomials which are monic inside fqx. Is there any question up to here? So this is actually very nice theorem. As I said, this is in every finite field book. So, okay, there is no question in chat, so I am continue. So okay, let's go one more further step, and I will try to count. So this was the first one, and I will try to count this one. So I, q, and 0. So this means I want an irreducible polynomial, but first coefficient is 0. So it is like degree n, but t1 is equal to 0. How many irreducible polynomials is there? And this is not very hard problem because of linearity. So first coefficient is trace, and trace is a linearity. So this is number of irreducible monic irreducible polynomials of degree n A1 is equal to 0. So if we just write, or just say T1, as I know, right? Okay. So how many of them? As I said, I will also mention about this. Actually, when we put extra term, we will start to use algebraic geometry, the curves, and also the third one. But I wanna just give you, if you wanna interest with this topic, just know what they are, how much easier, how much algebraic geometry we needed. So from here, as you see, the number theory and a bit of finite field knowledge is okay. But for this one, again, same idea with this linear thing. So you can find the number of this number. So I just first start with the easiest case, but we can prove for general, but I just want to emphasize the easiest case. If n and q is relatively prime, and then we can make a linear thing like this. So we can say x plus a for any a for a finite field power n plus say so as I said, let's assume the first coefficient is 0. Then the second one is a2 x power a plus n minus 2 and so on. So if we have such a thing, so let's write it in polynomial form. So x power n, we have n times a, x power n minus 1, and so on. So if n is relatively prime to q, this is not 0. And if I choose any other with 0, so I can get a non-zero one. For example, if I have the number of 0, I can actually get the others. Actually, all of them are same. So if I put here 1, any t1, doesn't matter. So for this one, for example, we can write over n for our linear transformation, and I will just get a here. So we can use this kind of linear transformation. So what is the difference? It is relatively prime or not? Because if it is kind of, I just write one example. If you take q power of this, we can get like q minus 1 as a polynomial coefficient. So this is x power q plus a power q. So here there is no x power q minus 1. So if this is n with which is not relatively prime, then we always don't get. So we can apply this linear transformation to get the non-zero coefficient for x power n minus 1. So because of this reason, this with this condition, it is much more easier to count them because we just divide this q because all of them are same. But if it is not relatively prime, so then how can we count it? So I start, as I said, I will again write r power, but q power n. But now I write here for making simple divisor of p, but I write n over d. D divides n, and here f. And as I said here, some alpha, maybe there is beta not inside of here, but let's try to count. So I denote a thing with fq and 0. This is number of elements in fq power n with our first trace, as I am writing trace 1, trace 2, trace thing, it minus actually, but say the trace 1 elements alpha. This one trace alpha is equal to 0. Okay, as I said, we can still, maybe it is not inside of FQM like this, maybe beta is not, but we can take its characteristic polynomial and think about its trace. So we relate this number with our number. So because counting those is much more easier, and like this, we relate them as an obvious thing with these numbers. So to do this, I will take, so for example, beta is a root of polynomial degree n over d. In this case, like beta, or like I will just say beta is equal to 0 with t is inside of irreducible word, monic irreducible word with degree n over d. Okay, this is also another thing. So it is irreducible polynomial, monic, and degree is n over d. Okay, so how can we find this relate? Okay, this is, we have trace of this, but we need to extend it here because we are looking to characteristic polynomials here. So okay, I will just write it. So we have p x power n over d because it is degree n over d, and let's define the first term as trace 1p, like t1p. This is not trace 1. Okay, so for, we call this like t, but when I am going down to emphasize, so this is trace 1p, okay. So it will be trace 2 and etc. Anyway, so x power m over d minus 1 and so on. Since we are just interested with the first coefficient, this is enough. So if I want to extend this to a characteristic polynomial, I just take the power d. So this is the reason I use n over d, because taking power d is make this numbers for vision better. So if we take the d power all of them, so our first coefficient will be x power m, and second one will be d times this. Of course, if we get more coefficient, it will get not like d times something, it will get more complicated. But for this one, it is not much hard. And going so on. So basically, I want this is equal to 0. Okay. And I will relate it with these numbers. So okay. Now, if this thing fq and 0 is equal, so we take d over n. For each d, we have a subfield, and in subfields we have irreducible polynomials, and we are checking the irreducible polynomials. So with number p inside irreducible d and over d, with, so I want this coefficient because trace 1 alpha is now this one, because this is a characteristic polynomial, and this coefficient is equal to this one. So e times trace 1 2 is equal to 0. Now there is two possibility, like here we separate it, but if p divides n, this idea wasn't very straightforward, but here if p divides d, this is automatically 0. So this is nice. So if we have a divisor of n, and our this p is our characteristic, so if also divides n, this is automatically 0. So basically, this is all of the polynomials. So this is because this is always true. So it is irreducible polynomials with degree n over d. In the second part, if p divides n and p doesn't divide n, so this means if p doesn't, they are relatively prime, so it has an inverse. Trace 1p should equal 0. So, and we are inside of irreducible polynomials like this, but degree is n over d, and the first trace is 0. So it is like q n over d 0. So kind of again we have Möbius idea. So this is not a standard Möbius thing. So need to do maybe some extra.
Emrah, I have a little question. So what do you mean by p device n? Like p, you mean q?
Sorry, d. Sorry.
No, I'm asking what is p?
P is characteristic of field. So we have. Oh,
I see. Because you use also p is like polynomial on the.
Oh no, this is small p. Okay. Big P
Yeah. Okay.
is,
Okay. Until now I was thinking q is actually just a prime, but it's also
okay.
prime power.
Yes, it is prime power and characteristic of a Q is.
Okay.
Maybe I should write all of them. Yeah, when we are writing kind of articles, they are they are different.
Sure. Just to be sure, my confusion. Right. Thank you.
Yes, I think. Okay, so as I said, this is not maybe a thing, but I really like this idea. I also like this maybe inside of in our question platform Math Kafası, and gives what happens if this kind of situation we can still apply the Möbius thing, and I write also in Turkish the proofs. If you want to check, you can check. Actually, I just write for many cases, so maybe most of them know, but the elementary number theory students or just interested them maybe don't know this kind of Möbius thing. So if we apply the Möbius idea, we get our IQ and 0. So it is just 1 over n some d device n p device doesn't divide p q n over d 0. And I use another notation like p device n, like this one. I hope you see this. So this notation is if p divides n, this is 1. If doesn't divide, it is 0. Sorry. If p divides n, it is 0. Sorry, 1. Otherwise, I think you see this one. Okay. So actually, when we are doing this calculation, it was just like the same idea because there was no p device, and actually all of them are same. So here, if q n over 0 is, let's check from here. And actually, we know these values, not counting. So in order to find this value, we just need to know all those. But these are easy because in a finite field, the trace 0 elements, just all of them, since because of the linearity, all of them is equal q power. So for this one, it is equal q power n minus 1. Because trace is linear map, so we have q elements and all trace number gets same number of elements. So this is actually q power n over d minus 1. So basically we know with this kind of sum, number of irreducible polynomial with trace is equal, so the first coefficient is 0. Any question? Okay, so I will go through fixing two coefficients. I don't want to clear this. Okay, so for two coefficient, actually we make this like trace 2p x power n minus 2, sorry, n over d minus 2 and so on. So here again the first coefficient will be the same because be the same. And this coefficient, if you want to get x power n minus 2, we get minus 2 or minus 1 minus 1. So choosing minus 1 and minus 1, two things. So this is d choose 2 and trace 1p. And choosing just only minus 2 is just 1, so it is d choose 1, it is d. As you see, we can write all of them, so it is just counting again number theory. Trace 2p and x minus 2. So with this idea, and again, if I want to count with 0, whenever I put some terms, it is just fixing, or this is trace 1 is 0, this is trace 2 is 0. So then fq and 0, 0 is just, I will do same calculation. Q device n, sorry, d device n with n over d. Again, we are multiplying with n over d because for each root we have, for each polynomial, we have n over d roots, different roots. So p is inside irreducible n over d with, I want this one is equal 0 and this one is equal 0. So d times this one. So again, we can write it like this one, actually similar. So if you go further, you can see it is not very hard. D divides n, p doesn't divide t. So if p doesn't divide t, from here it has an inverse. This means trace 1p should 0. So trace 1p is 0. This part is 0. D has an inverse, trace 2p is 0. Okay, then basically we have IQ, I just have to start from here, n over d. Since we get trace 1, p is 0 and trace 2p is 0, basically we are counting that. So irreducible polynomial degree n over d, first two coefficient is 0. And if p divides then this is trivially 0, and this is 0, and so here we should be careful because sometimes it is odd or even, so I don't want to share the even part for now. It is not very hard, just we can. So let's assume Q is off, okay. So again, this will be automatically 0. So we get 0 equals 0 always. So it is just every irreducible polynomial. I think I didn't write also another thing. Overview, irreducible polynomials. Same idea, but now we can again use maybe string to count them, and we get where it is 1 over n, v divide n, v doesn't divide v. Again, the question, so if I want to count all this, I need to count this, but trace 2 is not linear. We can say, oh, this is just q power n minus 1. It was, let's say it is q power n minus 2. So it is much more complicated. So when we are counting those, we will use algebraic geometry. Actually, we get supersingular curves. This is, I really know much more about it. So I am not, I can say I am doing algebraic geometry too much, but for supersingular curves, I am doing something. Not kind of a big algebraic geometry. Okay, let's try to count them. So we want the elements, so FQN 0, 0 is like this for general. So okay, we want to count for all, and actually n over d here, but we are just trying to count for each n this value. So we want, so we get an alpha from FQ over n, and we want the trace of trace 1 alpha is equal to 0, and trace 2 alpha is equal to 0. As I said, this is not very nice because the linearity, but here only this one actually we can relate with curve. But we have some nice things we also relate this with curve. So okay. So in a finite field, the characterization of trace 0 is just there exists an element, so we can write alpha as a c power q minus c. So c is also inside of fq power n. So we use this to put inside here. So this is characterization is easy, as I said, this q power n minus 1 elements here. Okay, this is not very hard, nice, but we will try to count trace 2 elements with this element. So how many such an element exists? And here actually we should be careful because, for example, if I add an element from FQ, say, I don't know, U inside of FQ, and it is again, because this is a linear map, so this is again equals in. So this actually, there is alpha is equal to this one, but there are Q elements like from FQ giving the same thing. So at the end we divided 1 over Q. We divided Q. I am not sure I will go further detail, but if we go to trace 2 alpha plus beta for in general, because we have something here as say alpha, this is beta. So it is not, we can relate it, this is not a linearity. We can say it is trace to alpha plus trace to beta, but it's like trace to alpha plus trace to beta plus trace one alpha trace one beta trace one alpha. So it is not hard to see, because when we are opening this with q power I plus q power j, so I and j different. So we can first take powers of this, they will give this one, and we have cross multiplication here, but we don't have diagonal. I can't be equal j. Actually, if you put this diagonal is this one, other part is just multiplying this and subtract this diagonal. So showing this is not very hard. So if you put here c and minus c, and always q power I plus q power j is for opting is given. Or again, if q is even, also it is even, but this is always given. So let's keep it in mind. So if we go for trace to c power q minus c, we just put here c power q, but taking q power doesn't change infinite field, so we will get trace to c here, and minus c, again, if you put minus, it will be plus, because this is given. So here again, we have c power q, again, we don't need q, it is just c, and minus in trace one, like we have just one, so it is all, we take minus out, we get minus sign here, and we just multiply here. Okay, so I will just write that we get 2 trace 2c plus, now here we have minus because of minus c, minus trace 1c square plus, because again we have minus c minus come here plus, and this is kind of c power q, and this is minus c, it will be c power q plus 1. So trace 1 c power q plus 1. So again, this same kind of diagonal thing, if we just do this, try to calculate this one, actually this is the nice part. Up to here, we can relate them with curves, because as you see, we can relate it with curves. I will just also write the curve idea here. And so the curve idea is trace of some f of x is equal to 0, and we can say that there exists like this one, and there exists y such that y power q minus y is equal to f of x. So this is the basic thing, is this is Artin-Schreier curve. So it is actually an algebraic curve. So, but here we will get also a supersingular curve. But we need, like this one, trace 1 is equal to 0. If trace 1 of some function is equal to 0, then we can relate it with algebraic curves, Artin-Schreier curves. Okay, so the nice part is this one. Again, I don't want to make the calculation too much. This one is minus trace 1c squared. Basically, trace is linear, so we can write it trace 1 c power q plus 1 minus c squared. As you see, we have trace 2, and we know that this kind of alpha should be written like this. And if we put this C power Q minus C, we get again trace 1. So we can relate this number with the curve like this. So basically, let me write the end of the thing. So FQ and 0, 0 is equal. As I said, we should divide Q from here, 1 over Q number of elements X inside of FQN with trace 1 C X Q plus 1 minus X squared is 0. So what now let's relate it with this curve. So it is equal 1 over Q squared number of the elements inside of curve minus 1, where C is YQ minus Y, X power Q plus 1 minus X squared. So here we divide extra more Q and take minus 1 out. I tell the reason. So we have an extra point coming from infinity. To take this, I just take subtract 1. And for each, so for example, if trace 0, okay, we have an element, but we have Q elements here. So it has a solution, but the same idea here, it has a Q solution. So we are not counting that, we are counting Q times of it. So I divide to extra Q it. Okay. So now we have the monic irreducible polynomials degree and first two coefficients are 0. They are related with these numbers, but if we look all of them, so not just, so here n is just a random number, but at that we see that this is related with this number. Actually, C is, I should have like this. So C, but number of rational points inside of FQN. Okay. So we related it with this curve, and we should count it as number of rational points inside of that field. And this is not very hard. We count it. This is supersingular curves. Supersingular curves are nice because if we take the roots of the L polynomial, so we are now going to algebraic geometry. So we have supersingular curves, we have their L polynomial, but the nice thing on supersingular, so the roots of L polynomial square root of Q times something, this something is inside of a unit circle, but this unit on unit circle, these are just roots of unity. So it will, you know, if you after a power, it just come to again 1. So roots of unity is nice because we have a period after a 1. So I don't remember, the period is sometimes here should be 2p or 4p. Depends on why Q is equivalent 1 or 3 inside mod 4. So if we go further, so we actually, there is one person, Kuzmin, proved this using, find this using Gauss sums, but here we are using number of rational points of this supersingular curve. But people try to count them using just finite fields. I like finite fields, I know finite fields, I think enough, but you can't do just finite field arithmetic to count such a thing. So if you, so there is actually a nice areas beside of, you know, finite fields arithmetic. So this is because there is a huge knowledge on curves, especially supersingular curves. Actually, this is, we can relate this with quadratic forms. So if you just check this one, this is a quadratic form in that finite fields. So actually we have a nice thing. So if you have such a nice thing, you can do much more easier the calculations. I just want to tell about when we try to count these numbers, and this is, say, R, not just 2, 0, 0, 0. So we now fix 3 curves. So here we get 1 curve, but to count this, again, we was lucky. We had 3 curves to count the number of rational points. One is y over 2. All of them are in Schreier. Let's write for general Q here, but for Q is 2 power R, all of them get again quadratic forms and supersingular terms. Because of this reason, 2 power R is better. So x power same curve, we get same curve, and this curve. So this is kind of a cubic form. I actually try to understand this again for 2. It is like in base 2, this is again have kind of quadratic style, but for Q is odd. How can I say? I don't know much more about. So we have quadratic form. Knowledge of quadratic form is huge, but kind of cubic forms, I really try to understand them, check some references and understand, but not much more people did something about this. So I don't know, maybe it is very hard, but maybe we should interest with some easy cubic forms. Okay, the third one is just addition of this. So if we can count number of rational points of these 3 curves, then we can understand this. As I said, if this is 2 power R, if the characteristic is 2, then all of them are supersingular curve and we count it. But for example, even it is 3, this is not supersingular curve. This 2 is not supersingular curve, because I also checked with mine, like we also use this periodic idea. People assuming that we will always get the periodic thing, because when they are doing some finite fields, they always find a periodic formula. But for Q is equal to 3, we don't have this periodic idea again. So this is kind of a counterexample if you put here Q is equal to 3. And one person showed that, so we proved that when it is 2, it is periodic. I don't know how he showed, but he used another idea and say that this is periodic only when the characteristic is 2 and 5. I don't know, I actually wondered why 5 is also special, because I don't see any reasonable reason that these are supersingular curve. There is 2 options, and one of them is 4, 5, and it will be really surprising for me. Both are supersingular, or the roots just, okay, they are not supersingular, but non-roots of unity just cancel each other. So there is 2 options, but if they are really supersingular, I will surprise. And for more coefficients, as I said, we can't relate them with curves, but my other co-author with this article made some progress, another article with giving the procedure, how can you make some, for some of them, how can you calculate them. And this is just what I want to say about this topic. I hope it will be nice for you, because I really, if you want to do something on this topic, if you want to continue, as I said, these are the people what they did, and Rob did some extra more if you want to read, and the other guy with different method show it is just the characteristic 2 and 5 is special, and so on. Thank you.
Thank you very much, Sercan. So let's thank Sercan with any kind of reactions you would like to show. Well, now I'll stop recording.